For the rest of the time, let's go back to vectors. And right off the bat, let's talk about vectors in 3 dimensions. U and V are the common letters in our textbook used for vectors. Again, like before, I'll put a little half arrow above my vectors. The textbook puts full arrows above. If I write my vector in component form, then I use the pointy brackets again. I write the components. If it's a 3-dimensional vector, I need 3 components. Call them U1, U2, and U3. Geometrically, this does correspond to a point whose coordinates are the same numbers, the same as the components of the vector. And what's one way to draw the vector as an arrow? Let me draw the positive x-axis this way, positive y-axis going in here, and positive z-axis going here. If the point with coordinates U1, U2, and U3 happens to be right there, if this is P, and pretend it's kind of behind the paper, so pretend U1, U2, and U3 are all positive. They are the x, y, and z coordinates of the point. The position vector of that point starts with its tail at the origin and ends the terminal point or head at the point P itself. And that arrow has components U1, U2, and U3. But with vectors, it is important for application's sake to allow yourself to move them around. As long as they have the right direction and length or magnitude, you still consider them to be the same vector. It's convenient to be able to move them around, to have, for example, forces in different spots. And maybe 2 forces are the same force, but they are acting in different spots. So they're the same vector, even though you draw them in different spots. And it's useful for motion, like we talked about before, like with the velocity vector, to put its tail at the location of the particle as it moves, so that it's pointing tangent to the curve. Always, as the curve gets drawn, the velocity vector always points tangent to it, and with a length or magnitude equal to the speed. It's a convenient thing to allow yourself to do that. What is the length of the vector? What is the magnitude of u, denoted by double absolute value signs? Magnitude of u, well, just apply the distance formula to the point P effectively compared to the origin. So what you're going to get is the square root of u1 squared plus u2 squared plus u3 squared. It's essentially the distance formula. But now we're not thinking of it as the distance between the point P and the origin, even though that is what it is. We're thinking of it as being the length of the arrow. And it's still the length of the arrow, even if I move the arrow around, because it stays the same length. Keep it this, it's a rigid kind of motion here. You can move the arrow, don't change its length, don't change its direction. Just move it in a rigid way. We're going to see next Monday that this formula can be written another way in terms of something called the dot product. But we're running low on time today. So unless we have time at the very end, we won't do that. But it'll be important for us to do that sometimes. Given any vector u like this, I can also create a new vector that has a length of 1, called a unit vector. Maybe it's unfortunate that we're calling this vector u. This is not necessarily a unit vector. It doesn't necessarily have length 1, but unfortunately we're calling it u anyway. The unit vector associated with u, as long as u is not the 0 vector, not equal to 0, 0, 0, so that I'm not dividing by 0, is obtained by taking u and effectively dividing by its magnitude. But what does that mean? What does it mean to take a vector and divide it by its magnitude? It really means multiply it by 1 over its magnitude, where this is a so-called scalar, and this is a vector, and the product is a vector. When you multiply a scalar, a number, by a vector, you get a vector, a rescaled vector. That's why that's called a scalar. As long as u is not the 0 vector, then we're not dividing by 0. But how do you do this multiplication? You do it component-wise. If I write out the components of u, effectively it's like distributing the scalar through the components. Multiply each component by the scalar. 1 over the magnitude of u is just a number. u1, u2, and u3 are just numbers. I've got the product of a bunch of different numbers here, and I'm putting them in a vector. That's the components of the new vector. As an example, and let's pick an example where the numbers, well, okay, I don't know if I can do it in my head. The numbers won't necessarily work out nicely. What if u is, okay, for lack of creativity, 1, 2, 3. What's the magnitude of u? It'd be the square root of 1 squared plus 2 squared plus 3 squared. There's our square root of 14 again. How about that? So the unit vector associated with u would be u divided by its magnitude, which will be 1 over square root of 14, 1, 2, 3. It'll be a vector with components 1 over root 14, comma 2 over root 14, comma 3 over root 14. And this will be a unit vector. It will have length 1. Why? Try it out. Take the magnitude of this thing. Double absolute value signs within double absolute value signs. For this example, that's the magnitude of this. Square root of the sum of the squares of these things. Ends up being the square root of 14 over 14. Square root of 1 is 1. It is a unit vector. It's got length 1. I multiplied the vector here by this scalar component-wise. It was a particular kind of scalar, but you can always multiply any vector by scalars, by any scalar in the same kind of way. If R is a scalar, and I'm multiplying it times a vector, I multiply component-wise to get this vector. And if R is a positive number, geometrically, that scales the vector. For example, if R is 2, then the new vector, 2 times u, points in the same direction, but it's twice as long. If R is 3, it points in the same direction, but it's 3 times as long. If R is 1/2, it scales it down. Points in the same direction, but it's half as long. If R is 0, it becomes the 0 vector. What if R is negative? If you plot things correctly, you'll see that the vectors get turned around. They point in the opposite direction. If R is -1, the new vector points in the opposite direction, but still has the same length. If R is -2, it points in the opposite direction, but it's twice as long. If R is -3, it points in the opposite direction, but it's 3 times as long. That's how scalar multiplication works geometrically. We also want to be able to add vectors like we did with I hat and j hat last time. U plus v, component-wise, If the components of U are U1, U2, and U3, and the components of V are V1, V2, and V3, how do you add them? You add them component by component. The new vector has first component U1 plus V1, second component U2 plus V2, third component U3 plus V3. Geometrically, if that's U and this is V, of course, I'm drawing these on my paper, so you could imagine these as two-dimensional vectors. But if you wanted to use your imagination with perspective, maybe V is going into the paper, so that maybe these are in 3 dimensions. Doesn't matter. You still interpret the sum geometrically according to the parallelogram rule. You first translate V over to the right until its tail is at the head of U. So this vector right there is V as well. Then you translate U over so its tail is at the head of V. This vector is U as well. And their sum, if you put the initial point, the tail, at the same spot as the original U and V, will have its head over here at the tip, the head of this U and this V. That will be U plus V. And this picture works whether it's a two-dimensional picture or a three-dimensional picture, where you maybe imagine V going into the screen, into the paper, and this is kind of like a plane going into the paper or screen as well. It's still the same geometric interpretation either way. You use this parallelogram to find it. Vector addition. Vectors can be subtracted as well. I could compute U minus V, and it can be interpreted geometrically. How? Think of it as U plus negative V. In other words, U plus -1 times V. In other words, V is getting multiplied by the scalar -1 before you add them. So if U is here and V is here, before I do U minus V, by interpreting it as U plus -1 times V, I'd want to multiply V by -1. So in other words, -1 times V or negative V would look about like this. And then I would want to add these two vectors, U and -V, by drawing a parallelogram. And again, the sum of U and -V would start at the same point that they both started with here and end at the opposite side of the parallelogram. This would be U plus -V, which is the same as U minus V. That's one way to interpret it geometrically, the difference, U minus V. However, it's not the most common way to interpret it. The most common way to interpret it is as an arrow that goes from the tip of V to the tip of U. Now, I didn't draw this very well, so these don't look like they're the same vector, but they are. That's supposed to be U minus V as well. Pretend these vectors are parallel, even though they don't look like they're parallel, and pretend they have the same length. If I drew it perfectly, they would. When you interpret it that way, then you're really interpreting it as the vector you need to add to V to get U. And that can be justified algebraically by canceling the V's. And it can be justified in a picture by adding even more to the picture. Like that. There's another parallelogram. Yeah, it's a little tricky. If I take V, this arrow here, and add on U minus V, this arrow here, effectively the parallelogram, you want to think of it, it's a little confusing. I think I better not try to explain it. But this is the vector that you need that's parallel to this original one, that when you add it to V gives you U. Vector addition and scalar multiplication satisfy a bunch of algebraic properties. Instead of trying to write them all down, which would take 10 minutes, let's look at them in the book. Algebraic properties of vector operations, meaning vector addition and scalar multiplication. They're all properties you would want to be true. U, V, and W are all vectors. C and D are scalars. First one, U plus V equals V plus W. That's called the commutative property. You can add them in either order. This one's the associative property. You can put the parentheses in either spot, which refers to order of operations. Here, this means do U plus V first before adding W. Here, this means add V plus W first before adding U, but it's the same thing in the end. That also means you don't need parentheses at all, actually, when you're doing vector addition, because it doesn't matter what order you add them in. This one is the zero vector is the additive identity. In terms of components, the zero vector is 0, 0, 0. Geometrically, it's just a degenerate arrow. It's just a dot, a point, an arrow with no length and no direction. If C and D are scalars, you can first multiply C times D, the product of those two numbers, before rescaling V, or you can rescale V by D before rescaling that vector by C. These two are distributive properties. This is careful that you think about these in the right way. The addition there is number addition. C and D are real numbers. The addition there is vector addition. CV and DV are vectors. Here, when you look at this equation, that is not the vector zero, that's the number zero. And this is the zero vector. Notice the little arrow above it. The number zero times any vector is the zero vector. Rescale a vector, any vector by zero, you get the zero vector. This one says you can factor out the scalar as long as you take its absolute value. And this one says the magnitude of a vector is zero if and only if it's the zero vector. All these properties are properties that you would want to be true. And fortunately, they are true. Do you need to memorize their names? Not for a test, you don't. I won't ask you to memorize their name on the test, and well, you can use a note card anyway, but you don't need to rewrite their names on the test. It is beneficial to try to remember them to some degree because it helps you when I mention them in class. I mentioned the commutative property. It's helpful to remember what that is. There are a few other things in the reading. You should make sure you read about, for example, standard unit vectors, I hat, j hat, and k hat now, as well as some applications to physics. Technically, you should be able to do these problems since you've had physics, though they are often kind of tricky.